is space-time? Space-time refers to a four-dimensional fabric that combines the three-dimensional space as we know it, but it also takes the idea of another dimension made entirely of time. Space-time can be manipulated and curved due to the special theory of relativity, formulated by Albert Einstein. He said that anything with a huge amount of mass can bend this fabric greatly, allowing other objects to feel that curve and revolve around the object like the sun. Anything with mass can curve the fabric of space-time, but it has very little effect on the sun. Yes, the Earth does technically move the sun a tiny bit, but it's negligible. Another thing to note is that gravity is not a force, rather a product that comes out of this curvature of space-time. Alright, so what I have here is a two-dimensional visual representation of space-time. So when this fabric has no mass laying upon it, it is called a flat space. But now, look what happens if I add some mass towards the fabric of space-time. It causes a very obvious curve that planets can revolve around, and this can act like our sun. So now what happens if I add, let's say, Jupiter to the mix? It revolves around the sun. And now, this is a 2D representation, so in real life, when it's 4D, the planets won't actually lose energy. So right now, they're losing energy and it stops spinning around the sun, but in reality, they don't lose energy. All right, so now I can take even more planets, and you will see that all these planets have a preferred direction. So even if they don't start off the same way, so I'm adding the entire solar system in, so if I make these planets go one way and these planets go a different way, they'll still have the same, a preferred direction. So let's see what that looks like. See, they all now revolve counterclockwise, which is also how it is in real life. Okay, so, but how does this explain the Earth, Moon, and Sun system? So let's say I have the Earth, and the Sun, and the Moon. So if I make the Earth go one way, you can see it revolves. But now what if I add the Moon? You'll see that the Moon is actually revolving around the Earth for a while before it, starts orbiting the sun. So let's try that again. Keep them really close together. And you can see that for a while, the Earth did have the Moon revolving around it. So right over there, you can see that the Moon is actually orbiting the Earth before, they go back to the sun. That curvature or product is what we call gravity, because planets and other objects can move around the sun that way. Gravity can affect the orbit of some planets too. For example, in the 1800s, Urban de Verrier discovered that Mercury had a precession orbit. He was trying to mathematically model the solar system and saw that Mercury's orbit was a little bit different from the other planets. He immediately knew that this was due to a smaller, unknown, and undiscovered planet, which he named Vulcan. Many astronomers and scientists started to look for Vulcan, but they could not find it. Einstein disagreed with that conclusion and theorized that this precession of Mercury was due to the sun bending space-time, which has a gravitational acceleration of about 23.93 times that of Earth's. This theory, the special theory of relativity, proved him right. Astronomers and scientists tested his theory, and they were able to understand it because they saw that the alignment of stars were a bit off than they were supposed to be during a solar eclipse on May 19th, 1919 because of gravity bending objects, light, etc. How can gravity and the idea of warping space-time be useful to spark innovation for technology in the future? Here are some ideas that are still being questioned by physicists around the world. Number 1. The matter-antimatter phenomena. Scientists believe that since the Big Bang occurred, there was an equal distribution of matter and antimatter. Antimatter is the opposite or mirror of its matter counterpart, such as a positron compared to an electron. These particles look exactly the same as their counterparts, such as mass, except they hold opposite key features such as charge. Yes, antimatter exists in extremely small amounts, but 1 gram of, let's say, positrons can cost $62.5 trillion. But antimatter can actually exist naturally. For example, did you know that bananas are not only radioactive, but they can shoot a positron an hour that quickly annihilates with an electron right after? So, if we find out more about the different aspects of gravity, we can crack this riddle. When antimatter and matter meet, they annihilate each other and leave just pure energy. Now that we know how the curvature in space-time works, we can use antimatter and antimatter accelerators, or even naturally in some cases, to see if it's any different from gravity on regular matter. But doing this is harder than it seems because measuring gravity at such a small scale is nearly impossible, though the theory of general relativity does say that they would react the same under gravity, or under the same gravitational acceleration. We would need to directly see antimatter in front of us to observe this. The first direct observation was when the scientists saw a cosmic ray heading towards Earth and wanted to see what happened when it made contact with Earth. He saw that the electrons were seen with their positron counterparts, and they behaved exactly like matter under the gravitational acceleration of the Earth. Another great example is when physicists at CERN created the first anti-hydrogen atoms using the alpha G apparatus. Number 2, quantum gravity. One way to understand just how important it is to discover quantum gravity is this. It is said that black holes' centers are so dense that they form singularities, which are points of infinitely dense matter. For example, do you see that model over there? If you were to take an object heavy enough to bend the fabric so much you can't see the fabric anymore, that would be the closest representation of a singularity. With our current understanding of gravity, we cannot incorporate the special theory of relativity into finding more about how singularities work. This is where quantum gravity comes in. We need to figure out how gravity works at a subatomic scale, where a curve so little in space-time would be almost negligible to comprehend just how we would get an infinite amount of matter from a giant star that collapsed under its own weight with just a finite amount of matter. Number 3, time dilation. Not only did Einstein theorize gravity, but he also explained that time is directly proportional to the distance. This is because the speed of light is always constant. So if you change the speed at which you are moving, then the time it takes for you to get there will be different from someone who started at the same point as you. This was proved in the Hafel-Keating experiment, where cesium atomic clocks flew across the globe on commercial jet flights. They started at the same place, yet when they came back to Earth, there were 2 different times shown on the displays. This idea of time dilation or time warping could revolutionize interstellar space travel in the future. Imagine traveling at the speed of light at 16 years old, coming back at 20 and wondering why everyone that used to be your age is now 65 years old. Time is never the same everywhere because time is relative, and Einstein proved that with his theory of special relativity. For example, time actually slows down as you get closer to a black hole because of its immense gravitational pull. Number 4, white holes. Einstein's theory proved a lot of things right. In fact, most of the celestial objects we are familiar with today were actually proven long ago by him, but were not found until later in history when we had the technological advancements to see and detect these.
These are the exact opposite of black holes
because they don't let anything into them. Instead, they reflect everything out. So let me share my opinion on white holes. Remember, this is just a theory by me. So this is my opinion. So since we talked about antimatter and the asymmetry in it, I have theorized that maybe there is a symmetry in the universe, but we just don't know it yet. I mean, who knows? Maybe there's a multiverse and most of the matter lies in our universe, while antimatter lies in another universe. There would still be symmetry in the multiverse, but not our universe. Or maybe there's a fifth fundamental force that would separate most matter into antimatter, which we think of to be matter today. This is similar of how I think of white holes, because since black holes exist, maybe the antimatter counterparts are white holes. They're not thought of to be the antimatter counterparts, but maybe some part of them are, and they're most likely to be out there somewhere, but we just don't know where to look, or rather how to look for them. Not only are white holes the only thing we haven't proven yet, but wormholes are also very important in the universe, a very important concept, and they're not yet found. Wormholes can be found when two black holes create a tunnel in between them. There are many cool things that come out of the theory of special relativity, whether it's time warping, black holes, white holes, wormholes. It's very important to understand how these things could revolutionize the future of interstellar space travel.